All right, welcome back. So let me extend our previous conversation where we introduced this idea of a variable x, and we said 2 times x is equal to x plus x. And we said this was capturing this very general property that, for example, 2 times 7 equals 7 plus 7, or 2 times 5 equals 5 plus 5. And so we can think of it as 2 times anything is anything plus anything, but we actually mean the same anything here, here, and here. They've got to be the same number. And so we use a symbol instead of the word anything. We use x in this case and say 2x equals x plus x. Now I could also have said 2 times y equals y plus y, because y is just like x. It's just a symbol which means anything. And I could have said, 2 times b equals b plus b. This is stating exactly the same fact as that, exactly the same fact as that. B is just a variable, so we use a single letter, usually lowercase, and that letter means, any value. So what about x and y? Sometimes we have equations and they don't just have x, they have, for example, x plus y. Well, we can explore this in exactly the same way. For example, I could make the observation 2 plus 5 equals 5 plus 2. And we know that's true. This is 7, this is 7. Was that a coincidence just because I happened to pick 2 and 5, or is there something more general going on here? Well, let's see. 3 plus 4 equals 4 plus 3. Yeah, that's certainly true. This is 7, this is 7. So it's looking like when I do addition, I can swap the order of these things and get the same number. Well, maybe that's a coincidence also. Maybe it's just because these added up to 7. Let's try something else. 123 plus 5, that's 128. Well, that's also 5 plus 123. So from those 3 examples, it sure looks like we have some sort of general principle here. This idea that anything plus something else is the same as that something else plus anything. In other words, we can swap the order of these things that we're adding and we get the same sum. And just like we did with, 2x equals x plus x, we would like to express this in a more general form instead of just having these 3 statements on our post-it note, so that when someone says, what's 8 plus 9, and we want to say it's the same as 9 plus 8, we'd like to capture the essence of these particular examples. And we can do that by saying if we take any number and we add any other number, we get the same thing as if we take that any other number and we add that any number. So this is a second algebraic equation. And literally all this is saying is, hey, if I pick any value, let me think of it as x, and any other value y, and I add them together, I get the same sum as if I take that second number and then I add that first number. But again, what this is a generalization or an abstraction of these particular examples. And so if someone asks me to say something about, let's do 7 plus 2, and they want to know how can I write that as something else, well, I could say, this is x plus y, so x is 7 and y is 2, and my boxed-in formula here, my equation, tells me x plus y equals y plus x. Well, y is equal to 2 and x is equal to 7. And there's my specific formula, 7 plus 2 equals 2 plus 7, and I got it simply by using this general formula. So this is another example of an algebraic equation. And this captures something that we call the commutative law. The commutative law simply says you can add 2 things in a particular order, or you can swap the order of the things you add and you get the same value. And here's how we can write that using our notion of variables. So this is another example of an algebraic equation, and it really just summarizes a general version of something that we know to be true in specific examples. So that's a second type of algebraic equation.